So, last class we were talking about free energy composition diagrams. We also looked at how to get free energy composition diagrams, calculate them, also correlate them to phase diagrams. We took for example an example of an isomorphous diagram, and then we looked at how at various temperatures GX diagrams can be obtained by calculation of the free energy as a function of composition at a given temperature, and from that we can obtain what is called the solidus and the liquidus compositions at each temperature, because at each temperature you can get what is called the equilibrium between the two phases, the liquid and the alpha, and from that in principle we can generate the whole liquidus curve and the solidus curve, basically taking all these liquidus compositions at various temperatures, getting the trace of all these liquidus compositions at various temperatures, similarly the solidus compositions at various temperatures. Today let us try to see what is the correlation between these GX diagrams, particularly looking at one particular parameter, which is the, let us say in any GX diagram, for example if you draw the free energy equation, if you remember we talked about XAGA plus XBGB plus omega XAXB for a regular solution model, of course, plus RT XA ln XA and so on, XB ln XB. This is what we thought is an expression for the free energy of any phase, and in this what is known is this is absolutely no problem. At any given temperature I can easily compute the last part. Similarly these two are the first two are basically the pure metal components. So it is this which decides to a large extent what is the type of phase diagram. For example, when you say an isomorphous diagram or a eutectic phase diagram or a peritectic phase diagram or even a monotectic phase diagram, they are all to a large extent decided by this. And let us see today how this influences the evolution of phase diagrams and see how we can see various phase diagrams with that particular omega as one of the component. For example, if you take an isomorphous system, all of you know there are certain conditions for you to get an isomorphous system. What are the conditions? It should have same crystal structure, and anything more? Atomic radius difference should be smaller, okay, and electronegativity, then, and anything else other than electronegativity, atomic size, structure, valence, okay. So these are what we call them as Hume-Rothery rules, which decide that you get an isomorphous system. And if you look at from the thermodynamic point of view, isomorphous system you have, whenever we are talking about isomorphous, we have two phases, a liquid and a solid. So whenever I say a liquid and a solid, you can call it as an alpha phase, let us say. For both of these phases I can write an expression like this, accepting that here instead of G alpha I will put G liquid, and this will be XAGA liquid, XBGB liquid, and this will be omega liquid of XA and XB, and so on. So when you write two expressions for liquid and solid, you come across two omegas, one for the solid, one for the liquid, and they need not be always the same. For example, if you take an example of a eutectic system, in a eutectic system how do you define a eutectic? Anything beyond that? It is an invariant reaction. Let me see what are all the possible ways of expressing a eutectic. One is, as you said, liquid giving two solids, it is an invariant reaction. Anything more? What is a eutectic? Melting point decreases. Anything beyond? When I say a system, AB system forms a eutectic, what do I mean? No, let us not bring thermodynamics at the moment. Whatever they are immiscible. Mixed in what state? And what about liquid?
It is completely soluble in the liquid state and insoluble in the solid.
Yes, need not be completely insoluble. So the definition of a eutectic is A and B are completely miscible in the liquid state, they are either partially or completely insoluble in the solid state. I hope at some stage you have read this. So if you have forgotten, please brush it up. Okay, this is the definition of a eutectic. Yes, am I right? So in the liquid state they are completely soluble, whereas in the solid state they are either partially or completely immiscible. So what does that mean? That means the omega for that particular AB system in the liquid should be different from the omega in the solid, isn't it? In case of a eutectic, they are completely immiscible or they are partially miscible, and that means there is a solubility limit. B dissolves into A only up to certain extent, A dissolves into B only certain extent, that means there is a positive omega there. Whereas in the liquid we are saying it is completely miscible, that means possibly the omega in the liquid state is either 0 or possibly close to negative or close to positive, but it is close to 0 because they are completely miscible. Whenever we say completely miscible, it means the omega is close to 0. Whenever we say they are completely miscible, that means they are neither repelling each other nor forming intermetallic compounds. Whenever they form intermetallic compounds, delta H is highly negative, that means omega is highly negative. So whenever we see an isomorphous system basically indicates you this. It indicates you this, that the omega of liquid is close to 0 and the omega of solid is also close to 0. That is when you get a perfect isomorphous system, which is this, where you have a temperature AB and this is a liquid and this is a solid. The moment you see a phase diagram like that, you should understand that this is satisfied. The moment you see that one of these is 0, the other one is negative. For example, let us take a case of omega s being 0 and omega L is negative. What does that mean? It means the liquid is more stable with respect to the solid. Liquid is more stable because liquid the free energy becomes more negative, that means liquid is more stable with respect to the solid. That basically makes the liquidus plunge down. What you see the pseudo eutectic kind of phase diagrams, that where you see this kind of a phase diagram is a result of this. It remains still isomorphous, but the liquid stability regime is larger now. So the liquid exists over a range of higher range of temperature when compared to what you see in a normal case like this. So the liquidus goes down, and that gives you an indication that liquid is more stable with respect to the solid. And if you take another case where omega L is 0 and omega S is negative, then you get a congruent melting. This is what you see. You get a situation something like this. The solid is more stable with respect to the liquid. So solid tries to be existing up to higher and higher temperatures, and you immediately see a phase diagram like this. So the moment you see a phase diagram, it gives you an idea, even without doing calculations, it gives you an idea of what would have been the thermodynamic parameters for both the liquid and solid. Now we have looked at only the negative aspect of it. Now if you think of a situation where if we think of a situation where the omega L is 0, but the omega S is positive. That actually means that both the A and B, there is no attraction between them, there is some repulsion between them, and this basically means there is a tendency for segregation. A does not want to dissolve B to a large extent, and B does not want to dissolve A, and this actually leads you to what is called a miscibility gap in a phase diagram. For example, if I draw a isomorphous, you suddenly start seeing a miscibility gap. If I try to correlate this with respect to what we talked about Hume-Rothery parameters, let us take one parameter such as a size factor. You know that isomorphous actually happens when, of course, this is more of a empirical rules, but in a large number of systems this is valid when the size factor, which is called the delta, delta is nothing but the atomic radius of the solvent minus the atomic radius of the solute divided by the atomic radius of the solvent, the absolute value of it. If this is less than 8%, that is when you have a complete solubility. When you have, let us say, a particular A B, let us take a case of simple case of, let us say, copper gold, they are completely isomorphous. Instead of copper gold, I add copper aluminum, let us say, both are FCC, but you do not see a isomorphous between copper and aluminum. The reason could be because of many factors, and if we think that it is the size factor which is affecting it, let us assume a case of A B system with the size factor of around 10%, let us say. Then what you suddenly see is that because the size factor is larger, the A dissolves whenever a solute goes into the solvent, as long as the solute size is closer to that of the solvent size, the strain that is generated is very, very small. Whenever you imagine a case where you have a lattice structure like this, imagine that these are all the atoms of of the solvent, and suddenly I want to put a solute inside this. Assume that these are all of the same size, though some of these do not look like that, ignore that, and now you think of a solute being put here. If this solute is of a smaller size than that of the solvent, then what you see is it tries to, in order to maintain the bonds, it tries to pull the atoms which are around it, and that creates certain strain. Every 1% of the solute that you keep on putting, you will keep seeing that there is certain amount of strain that is generated, and as you keep on increasing the amount of solute, the strain that generated keeps on increasing, and any structure can accommodate up to certain amount of strain, and the more close packed the structure is, the less is the amount of strain that it can accommodate. That is why BCC structures can easily accommodate more strain, whereas the FCC structures do not. Of course, again it depends on whether we are talking of what is called substitutional solid solution or interstitial solid solution. Many of you remember that carbon goes more into an FCC structure than into a BCC structure. Though FCC is more close packed than the BCC, you see the amount. What is the solubility of carbon in FCC iron? 2%. What is it in point? 0.025 is the maximum in a BCC. So you see almost 80 times higher. This large quantity is basically because you see the voids, because it is an interstitial solid solution, the void size in an FCC, which is the octahedral voids, are much bigger than the biggest void that is available in the BCC, which is the tetrahedral void, and as a result, because the voids being bigger, the carbon can go and sit. And in fact, if you look at the actual carbon atomic size, the size of the carbon atom is much bigger than the void size, and that is the reason why you do not see 100% solubility of carbon in even FCC iron, only 2%. And that if you compare with many substitutional solid solutions where you have isomorphous phase diagrams, you do not have an isomorphous phase diagram with an interstitial solid solution. It is impossible, because the only 4 elements that we talk about which can actually go into the interstitial solid solutions, which are these elements? Yes, these elements that we talk about, none of them have their sizes which are so small that they can actually completely dissolve by 100%. The strain generated is sufficient enough that even if you put large quantity of this, the strain can be accommodated. So if you look at the strain that it is, if you can think that there is a critical strain epsilon star which a structure can accommodate, and if you think that there is particular strain called epsilon 1, which is the amount of strain that is generated for every 1% of solute being going into the solvent, you can say this multiplied by this cannot cross this. This is the maximum that the solute can take. So if this is larger, that means if the strain generated for every 1% of the solute is larger, then this has to be smaller for a given structure. For example, if I take a copper as a solvent and keep on adding elements such as aluminum, lead, and all other FCC elements, depending on the size factor between the copper and any of these solute atoms, you see the one which has a higher size factor, the solubility limit of that particular solute will be smaller, because this, if this is larger, then the maximum solute that it can go is smaller, so that this cannot be crossed. This is the maximum, because the moment you cross this, then what the solvent does is it cannot take the solute anymore, so it starts rejecting it out, and once it is rejected, you get various precipitates. For example, in copper aluminum you get CuAl2 and things like that. So in different phase diagrams you have different phases coming out, so that limits what is called the solubility limit. So there is a critical strain any structure can accommodate, and in fact this is what is also a reason when you keep on putting more and more defects into a system, a crystal structure can even break and become an amorphous. A large number of people have studied this, what are the conditions under which a crystal can become amorphous. For example, there are experiments where people have done taking a crystal and putting it into an electron microscope and keep on bombarding it with electrons, high energy electron beam. Particularly people have done these experiments with high voltage microscopes. I do not know whether you are aware, there are microscopes which are 1 million volt microscopes, 3 million volt microscopes, 3000 kV, in comparison to what we regularly see 100 kV or 200 kV or 300 kV microscopes, we are talking of 3000 kV microscope. And when you have such a microscope where the electron beam of that energy falls onto a sample, obviously it disturbs the atoms, and as a result you can have a large number of vacancies that are generated inside, and if this concentration of vacancies keeps on increasing beyond a limit, the structure becomes unstable and it becomes amorphous. So people have seen cases where even an ordered structure, people have a very interesting example people have taken is Ni3Al, which is an ordered structure. Do you know what kind of an ordered structure it is? Anybody knows? It is an FCC structure which is ordered, and when it becomes ordered, what do you call that structure? It is called L12 structure. Some of you who know about structures, it is called L12 structure, and this L12 structure where you have the nickel atoms occupying the face centered positions and the aluminum atoms occupying the body corners, because it is Ni3Al, 3 atoms of nickel and 1 atom of aluminum. This structure, when they have taken and put it into such a high voltage microscope and with more and more dosage of this electron beam, they saw that slowly this ordered structure becomes disordered structure. That means the superlattice changes into a disordered structure. That means whatever superlattice reflections that you usually see in an ordered structure, they slowly start vanishing. If you in situ you can see this in a TEM. So keep on observing how the diffraction pattern changes. You see that superlattice reflections slowly vanish and only the fundamental reflections you see. That means the ordered structure has become a disordered crystal structure, but still it is structurally ordered. Whenever you talk of disordering, many of you might know that there are two types of disordering we talk about: structural disorder, chemical disorder. So whenever I talk about ordered compound, I am talking of a chemical order there. When I say structural disorder, it basically means a crystal structure becoming into an amorphous structure. That is a structural disorder. When I say chemical disorder, that basically means in a chemically ordered compound, you have specific positions for each of the atom. Let us say in this Ni3Al, just now I told you that nickel occupies the face centered positions, the aluminum occupies the body corners. If the aluminum and nickel randomly occupy the atomic positions inside the crystal structure, the crystal structure still will be FCC, but it will not be called an ordered crystal anymore. It will be a disordered compound, because nickel and aluminum, the probability of finding it at any place will be equivalent to 0.25 and 0.75 depending on the amount of it, but I cannot pinpointedly say that this is where nickel is sitting, this is where aluminum is sitting, but in an ordered structure I can pinpointedly say this is where aluminum is there, this is where nickel is there. And so such a structure is a disordered structure chemically, but structurally still it is ordered in the sense it has a unit cell, it has a FCC unit cell. So the difference between this chemically ordered and chemically disordered is only in terms of the diffraction patterns. You can recognize, you will see extra spots called superlattice reflections in a chemically ordered structure, and in a chemically disordered structure you will not see these extra spots, and you would only see any of you who have read X-ray diffraction will know more about it. And now if you take that and if you continue to bombard it, people have seen that disordered Ni3Al finally becomes an amorphous structure with 75% of nickel atoms and 25% of aluminum atoms, which are randomly there sitting inside without any unit cell. So the unit cell breaks from a SCC unit cell to a structure which is similar to that of a liquid, and people have seen this happening, and that is all because there is a critical strain that the structure can take. So if you look at from a physical point of view, it is like this, but if you look at from the thermodynamics point of view, we are looking at only from this, and you know that the more the strain is, when will the strain be more? When the size factor is more. So the larger the size factor, you will see the larger will be the omega s positive. Sorry, I am extremely sorry for this. I don't know why this is. So you can see that the moment size factor increases, if the delta increases, then you would see omega s increases, higher and higher repulsion between the A and B, because as the size factor increases, then the strain increases. If the strain increases, obviously the repulsion increases. So now we do not look at this part, we simply look at what happens if the omega s increases. So the moment omega s is positive, what you see is suddenly you see a miscibility gap. As long as the size factor is less than 8%, you will never see this miscibility gap. The moment size factor crosses 8%, you start seeing a miscibility gap. That means what? That means there is a limit on the amount of B that can go into A. So only up to this much a B can dissolve into A, and only this much is A can dissolve into B. And whenever you see a solubility limit of A in B and B in A, you would see that this solubility limit keeps on changing as you change the temperature. Why?
Thermal energy vibrates the atom lattice position,
so
because of which it can accommodate.
Yes, this epsilon star would change as a function of temperature. The strain that a structure can accommodate, because the lattice expands as the temperature increases, isn't it? Because the lattice has expanded, so it can actually accommodate more and more strain, and as a result you would see as you increase the temperature, the solubility limit keeps on increasing. That means the amount of B that can dissolve into A keeps on increasing up to a particular limit, beyond which they are completely soluble. A becomes completely soluble in B and B becomes completely soluble in A. And similarly, on the other side also, the solubility limit of A in B also keeps on increasing, and you would see that it will finally meet, and this is what is the final temperature above which you can say completely they are miscible. And for a given omega, this temperature is going to be fixed. Now for example, if you think of a particular value of omega, let us say talk about 10 kilojoules, and now you increase it to 20 kilojoules per mole, both being positive, what should happen now? When you increase the omega S from 10 kilojoules to 20 kilojoules, what should happen? Yes, the miscibility gap should widen. Why? Because the A and B are more and more repulsive, they are no more attract. So as a result, the solubility of A in B and B in A should further go down, because A and B are they repel each other to a larger extent, and as a result what you see is that this miscibility gap increases. And the moment miscibility gap increases, I mean in other words, that when I say, that means size factor has further gone up. When the size factor further goes up, this is what happens. If the size factor goes up here, what happens is this will go up. If this will go up for the same structure, because we are assuming that our solute is the solvent is the same. If the solvent is the same, solvent has a fixed structure, so the total strain that it can accommodate is going to be fixed. So the epsilon star gets fixed the moment I fix up my solvent. What I am changing is only the solute. I am adding different solutes, each of them have a different size factor, that means each of them have a different omega positive. I am adding a different solute every time with a higher size factor, such that its omega S is more positive, and that means the moment this is higher, because this is fixed, this has to be lower.
So then why the temperature is?
That is what. So we will come to it. That means what you would see is that because this is fixed, okay, and at the same time you would see that the solubility limit on both the sides has come down. That means the strain that each percentage of A when it is added to B, or each percentage of B when it is added to A is increasing, this value is increasing. As a result, for the same amount of this structure, when you are increasing the temperature, this strain that it can accommodate is fixed, this is fixed. But as you are increasing the temperature, because this strain is larger, the temperature to which you have to heat so that this strain gets accommodated has to increase. As you keep on adding an element with higher and higher size factor, the temperature above which they completely dissolve into each other should keep on increasing, and that is why you would see that not only that the solubility of A in B and B in A decreases, but also you would see the miscibility gap will go to a higher and higher temperature, and you would see that the moment you start seeing bigger and bigger miscibility gaps, it basically indicates that this is the thing. But simultaneously you would see something else also happens in the phase diagram. Whenever you consider omega liquid being 0 and omega S being positive, you would see that not only that you develop a miscibility gap, but something happens to the liquid S curve also. What you would see is, because the omega is positive and omega L is 0, so with respect to the solid, the liquid is more stable, and as a result what you would see is that in addition to this, you would see that this liquid S curve starts plunging down, because with respect to the solid, now the liquid is more stable, liquid is more negative with respect to this. If this is positive and this is 0, that means it is more stable. So as a result, liquid comes down, liquid is stable for over a larger temperature range, and once this happens, you would see that there is a particular condition at which both this miscibility gap and the liquidus merge into each other, and once that happens, you would see a situation where the phase diagram actually becomes and you would see both of them merging into each other, and once they merge into each other, what you end up is nothing but a eutectic. You would see this is nothing but the eutectic point. These two are the compositions where you have actually the maximum solubility of B in A and maximum solubility of A in B. So you can see an isomorphous system suddenly has become a eutectic system, just because I have increased the omega s to a critical value, and this at what omega this happens actually depends on system to system. Each system you have to calculate, and but at a particular omega you would definitely see this happening for everything. And now if you keep on increasing it further, more and more omega, what should happen to this? You would see two things happening. Let me see what are your answers. Yes. So what does it mean? It means that the eutectic temperature goes down. This is what we call them as deep eutectics. Whenever you see a deep eutectic, what we mean a deep eutectic? In fact, people even quantify this eutectic because it is very important when people talk about glass formation. I will tell you an example. For example, if you take two cases, one where the eutectic is like this, another where the eutectic is like this. We call this as a deep eutectic when compared to this, and in fact people try to quantify this in terms of what is called taking the two pure metal melting points, calculating, drawing them by a straight line, and finding out what is the liquidus temperature as a rule of mixtures of these two. That means at the eutectic composition, what should be the liquidus temperature if a liquid A and liquid B mixture is available, let us say, and that with respect to this. So we call it as TL mix minus T eutectic divided by TL mix as a parameter, which people define it as a glass formation parameter. Why it is important is, when does a glass form? We said glass forms whenever a liquid is undercooled to an extent that it is brought below the Tg. In any system, the Tg is somewhere here. Glass transition temperature can always be calculated for a given system, and usually a glass transition temperature is somewhere around 200-300 degrees depending on the particular system. Of course, there are some systems it can be even lower when the liquid is very highly stable, and then you won't see the glass formation easier. So if you think of a glass transition temperature somewhere, if you have a phase diagram like this, it means the liquid, for it to be undercooled to get a temperature to Tg, the temperature that you need to undercool is much smaller than here, where the undercooling that you need to provide is very large. That means the cooling rate that you need to provide for the liquid to undercool to the Tg is much larger here when compared to the cooling rate that you need to provide for the liquid to undercool to Tg. That is why in a deep eutectic systems we can always say glass formation is easier. So that is why these are called easy glass forming systems, these are not so easy glass forming systems. So even with slower cooling rates, people are able to achieve glasses. For example, something like a silicate glass that you see, a silicate glass can easily form a glass even at a very low cooling rates, as low as even 0.1 Kelvin per second, whereas normal metallic glasses you need to go to 10 to the power 6 Kelvin per second to in order to be able to get that. That is the reason is because most of them, but even there also if you look at phase diagrams, look at a number of phase diagrams, wherever you see a deep eutectic, for example the first metallic glass, anyone knows which is the system where people have got first metallic glass? No, gold silicon, correct. Gold silicon is the first metallic glass in 1959. Paul Dewey has obtained it, and this gold silicon, if you compare it with simply like something like an aluminum silicon, today evening if possible go to the phase diagrams handbook such as Masalsky and try to compare gold silicon with aluminum silicon, you would see that this is a much deeper eutectic than this, and that is the reason why you get a glass more easily here than that. You take a simple aluminum silicon liquid and of the eutectic composition simply quench it, you would not be able to get a glass there, whereas here if you quench that liquid you can get a glass. So that is basically because this is deeper eutectic, and people have given a condition that if this value is greater than 0.2, by looking at a number of systems, people have said that if this value is greater than 0.2 then you can say it is a easy glass forming system, otherwise it is not so easy glass forming system. Of course these are thumb rules like Hume-Rodary rules, more of empirical rules based on looking at a number of systems, and people have come across certain values like that. So this is one of the glass forming criteria. There are a number of them, we will talk about them as we go along a little later. So just because this concept came, I had to tell you this. So as you can see that if I keep on increasing omega, you would see this goes down, and as a result you would see that the liquidus temperature goes to lower and lower value. That means eutectic temperature goes to lower and lower value. And anything else that happens?
It gets more wider.
So that means the solubility limit of A in B and B in A also starts decreasing further, because this increases means this becomes more. So that kind of thing you would see. So the because the miscibility gap becomes wider and wider, so solubility limits keep on decreasing to an extent that at some value you would see that the solubility limits vanish, something like this. You would see a phase diagram becomes something like this, where there is no solubility of B in A or A in B. It is like a liquid giving A plus B instead of liquid giving alpha plus beta. There is a difference between the two, isn't it? When I say liquid giving alpha plus beta, that means the two are terminal solid solutions. That means there is a solubility of A in B and B in A. So instead of a phase diagram like this, you end up into a phase diagram like this, something like this, where there is no solubility of A in B. So the moment you see these things, you can get an idea of this, and people actually even do the calculations to be able to find out whether it really happens or not, and a number of people have already done this. And as I told you, even we have a journal which is available called CalFAD, which regularly does this kind of calculations. And now let us see what happens if the omega L is positive. Yes, pure iron, okay. It is because of the magnetic transitions, in principle that iron is BCC at room temperature, and then it changes to FCC, and then in fact if you carefully observe, most of the actual metals, when you go to a higher temperature, the phase that is more stable is the one with a more open structure. You regularly see this happening in for example titanium, okay. High temperature phase is a BCC phase. In most of the structures, the high temperature phase is always a BCC phase. Even if you look at things like ceramics, barium titanate, you take high temperature phase is always a cubic phase, low temperature phase is a tetragonal phase. Even if you take zirconia, titania and yttria, all these things you see this kind of things. Whereas here, because there is a magnetic transition, that interferes with that. So, as a result you get that, and because that phase is actually not a closed packed structure, is not really stable at high temperature. So, when you further heat it to higher temperature, it comes back to a open packed structure, which is a BCC structure. So, the intermediate FCC structure is a result of actually magnetic transition in this material, otherwise you would not have seen this. Okay. So, now if you look at this case of if I assume a case of like this, which I cannot actually assume, this actually looks absurd to anybody. But why should it look absurd? When I say omega s equal to 0, omega L is positive. You say that when you say omega L is positive, that means A and B are repelling each other in a liquid state. If A and B repel each other in a liquid state, automatically they actually repel each other in the solid state also. It is very, very difficult to imagine that A and B are having an ideal kind of a situation. They neither repel nor attract in a solid state, but in the liquid state they repel each other, because liquid is a more open structure. In a more open structure, actually A and B should dissolve more easily. That is why we see whenever I say eutectic. By the way, when we talk about the eutectic formation from an isomorphous, you can also get a peritectic in the same fashion. The difference is you get a peritectic when the melting points of the A and B are largely different. Same way you can construct and you can get a peritectic phase diagram from an isomorphous phase diagram, excepting that the peritectic happens when the two pure metals. For example, whenever you see a peritectic, a good example is copper zinc. Let us say copper zinc is a classic example of what people call it as cascade of peritectics. You have a number of peritectics in a copper zinc. Copper tin is also another such example. The reason is one of the element copper melts at a much higher temperature than the tin, which melts at let us say 232 degrees centigrade or so. So, when you see these large differences in the melting points, then instead of a eutectic you see a peritectic happening, and you would see, if you go back to any of the phase diagrams, you will see this happening. Now, coming back here, you see that if this has to happen, hypothetically anything can be assumed. If you assume this hypothetically, what it means is, if the omega L is positive, that means there is a miscibility gap in the liquid. Have you heard of miscibility gaps in the liquid? Where do you see miscibility gaps in the liquid? Monotectic phase diagram is one. Of course, the extreme of this is a syntectic. So, monotectic, for example, if I draw a monotectic phase diagram, what is a monotectic phase diagram? This is a monotectic, that there is a liquid and here you have L1 plus L2. So, what does this reaction mean? L1 gives you, what is the monotectic reaction? How many of you remember? Yes, liquid gives another liquid plus a solid. This can be an alpha, this can be a pure metal, depending on the situation. Most of the cases the solubility of B in the solid in many of the monotic systems is almost 0. So, we can simply say that this gives you a solid A, let us say A or B, depending on which side the monotectic is. So, that means this phase diagram can be replaced by something like this. That means there is no solubility on this side, and as a result you can say liquid gives A plus liquid 2. And now, whenever you say liquid 1 gives you a solid plus another liquid, that means below the reaction, and again this is also is an invariant reaction like what we have seen earlier. Why it is an invariant reaction? Why 0 degree of freedom? 3 phases we have, and it is a binary system. It is a binary system, number of components are 2 and you have 3 phases involved. Why I say 3 phases? Because there are 2 liquids What is the difference between these two liquids? Concentration. Okay. The composition of L1 is different from composition of L2, both having the same structure, both have the same structure, they are all, both of them are liquids. So, they have random arrangement of atoms, but they have two different compositions, and the moment I say two different compositions, there is a boundary between them, and as a result I have to define it as a separate phase. So, that is why like here when I say a miscibility gap in the solid state, what is there between within the miscibility gap? Two solids, we call them as alpha 1 plus alpha 2, and interestingly both of them have the same structure, because on the both the sides two pure metals have the same structure, otherwise you would not have got an isomorphous system. The fact that it is isomorphous, it indicates that A and B have the same structure. We are only talking about A and B having the same structure, but with different atomic sizes, such that you are getting a miscibility gap, or with whatever may be the parameter, whether it is atomic sizes or valency or electronegativity, but ultimately giving to a positive omega s. We have only taken a size factor as one of the parameter, because it is easy to see, because it is easy to understand based on the strain, whereas the other two I can also choose electronegativity or valency, but again the same thing has to, basically everything gets reflected to this. If this becomes positive, you get, though A and B have the same structure, you get a miscibility gap, and within that both the alpha 1 and alpha 2 that you see have the same structures, but excepting that their compositions are different. That is why if I draw at any given temperature a tie line here, these 2 points represent the composition of alpha 1 and composition of alpha 2. Exactly similarly, if I draw at any given temperature here, these two represent, this is the composition of L1, this is the composition of L2, and at the peritectic at the monotectic temperature, L liquid of this particular composition is giving you another liquid of this composition, and because below the monotectic there is a liquid that is available, because one liquid is giving you another liquid, this liquid which is coming out of the monotectic has somehow to solidify. So, as a result, many monotectic phase diagrams you would see, in addition to a monotectic reaction, another additional reaction where the liquid which comes out of the monotectic solidifies by either a eutectic reaction or by a peritectic reaction. So, that is why you would see here an extension of it, you would see either a eutectic reaction. So, that means here the L2 that is coming out. So, here you can say it is A plus L2 below the monotectic reaction. So, liquid gives you, and this is what is this phase field? A plus L1. So, you will have A plus L2, and this L2 will undergo a eutectic reaction or a peritectic reaction. In this particular case it is a eutectic reaction, and as a result below that eutectic reaction what will you have? A plus B simply. That is how we can see. Whereas if it is a eutectic reaction or a peritectic reaction, you need not have to have another reaction. There can be phase diagrams where you can have a number of various reactions like iron carbon, where you have a eutectic, a peritectic, and a eutectoid, but there are also systems where you have only one simple reaction. For example, aluminum silicon, it has one single eutectic, nothing else. Magnesium silicon, you have two eutectics, nothing else. So, there are also systems like that. So, you will see whenever you see a monotectic, you will see things like this, and this monotectic is caused by what? The omega L being positive. Whenever omega L is positive, there is a miscibility gap inside the liquid, and once there is a miscibility gap inside the liquid, you lead to a monotectic reaction, and that is how we can understand. And the more the omega L becoming more and more positive, it finally leads you to a syntectic kind of a case where they are completely insoluble in the liquid state and also insoluble in the solid state. You rarely can think of a situation where they are completely insoluble in the liquid state, but soluble in the solid state. Reverse is possible, that you can have a complete insolubility in the solid state, but solubility in the liquid state, which is what is our eutectic. but you will not see a situation. That is why whenever there is a syntactic that there is a complete insolubility in the liquid state, you also see that in the solid state there is complete insolubility, and that is how we can see just based on these two parameters we can evaluate phase diagrams. We will stop now.